people started developing quantum gravity, because at those smaller scales, you're supposed to start seeing quantum effects. So you need theories of quantum gravity to try to explain that. So, for instance, you need to understand these effects if you want to understand what happens near black holes, what happens to the information that goes into black holes. Does it come out again? What happens to what's inside the black hole? What is inside the black hole? We have no idea. What happens to the singularity that is supposed to be inside the black hole? Is it formed? Does it exist? Does it not exist? These are all theoretical puzzles because we have absolutely no way of observing them yet.
Hello and welcome to SciLux, the podcast where we usually talked about science and developments in Luxembourg. But as you know, now in season 6, we're focusing on all the science done in Europe. So the podcast is for people who love science or those ones that don't know yet that they do, as I like to say. So hopefully after today's discussion, you will love science even more. I'm pretty sure this will be the case because our guest today is Dr. J. Armas, who is a theoretical physicist and science communicator. Jay works at the University of Amsterdam and Niels Bohr Institute in Copenhagen. He also coordinates the Dutch Institute for Emergent Phenomena, and he founded Science and Cocktails. Jay, thank you so much for coming today.
Thanks for having me.
Once again, I have a guest that makes my life very difficult because I start reading about all the stuff that my guest does. And then I'm like, oh gosh, it's like I need 5 podcasts or 10 podcasts because you've done so much in science communication and in physics and in so many other things. So first of all, let's say I give you a stage right now. You stand in front of the general audience, as we like to say, or lay audience, and you have one topic to talk about right now in science. What would it be?
Well, I think it will depend on how long I have.
Important.
But let's say that I have sufficient time. I think I would speak about the topic of emergence. And this is because it's just a concept, an umbrella of ideas that would sort of encompass almost everything that I like. So, the origin of the universe, the origin of matter, the behavior of black holes, and even things like social phenomena or the way that living systems work. All these kind of things would be sort of manifestations of the same concept of emergence. So I would explore that, I think.
I love the fact that you gave me a term, because that's also one of the questions of science communication. When you have something complicated, would you mention that you're talking about emergence or not? In the sense that, if you get on the stage and you say, now I'm going to tell you about emergence, and everybody's like, oh. Would you mention the word?
Yeah, I would mention right away the word. And of course, I would define it. So the concept of emergence is rather simple. So you can have, let's call it a system, something that is composed of many individual things. It can be, what physicists like. It can be small particles. It can be what the string theorists like, and that would be small strings. But it can also be, a group of people. It can be a group of birds. It can be a group of cells. And these cells or birds or people or atoms or particles, they have some interaction rules. They behave in a certain way according to certain laws that we know of. And in some cases that we still don't know yet exactly what they are. Like in cells or people, that we don't have a general theory of that. But we do have a general theory of particles and sometimes also of strings. And depending on those interaction rules, if you put many of them together, many of these particles, many of these people, and you zoom out at larger distances, you start seeing completely different kind of behavior than the behavior exhibited by the small particles or atoms or people. So you can have, let's say, crowd phenomena. You can have people moving as if they're flowing as a fluid on the street. You can have cars also sort of flowing. If you, for instance, imagine the experiment in which you put a camera on a highway from the top and you film that highway for a long time, and then you take your recording, you fast forward it, and what you see is that you don't see individual cars, but you see a stream that looks as if it's flowing. So somehow, when you zoom out, you find emergent behavior. You find something that emerges out of the small interactions or the interactions between the small little elements that you have in your system. So it's a very simple concept that sort of encompasses almost everything, because the universe also came out from somewhere, and you need to identify where it came from. What are the small elements that it gave rise to the universe itself, or of black holes, or even like a kettle boiling with hot water. So everything is in there.
It is a fascinating concept, and my intuition tells me that it is very difficult to quantify. Am I right? Like, can you actually predict it? Can you have an equation of that flow?
Let's say if you really want to understand emergence, you take a small system that you know the rules, and you want to sort of zoom out and look at the emergent behavior. In general, it's an extremely difficult problem. And in fact, that's why, in some people would even say there's separation within physics. So in physics, we have many subfields. We have particle physics, then we have the physics of materials, then we have the physics of biological systems, then we have the physics of the astronomical objects that we have in the universe. That's within physics. And then we have all the other sciences. Then comes chemistry and biology and psychology and sociology. And the reason why these things are not just one single unified thing is precisely because it's very difficult to go from the smallest particles possible to a human being. So in general, is a very difficult problem. But in physics, and in certain other systems as well, we actually have control over it. We can define the system of small interacting things in such a way that we can actually go from that small system to the large macroscopic description. And in fact, there's many examples of that. One of them being, for instance, gases, the theory of gases. At the small scale, you describe it as a bunch of interacting molecules, or atoms if you want, some elements. And then you can sort of look at this system in the entire room that you're in right now, and you describe that with a very simple law, the ideal law of gases. And that's a way of flowing from the small scales to the large scales. But in general, is very difficult. And whenever you can do certain things like that, there's a kind of breakthrough in science. So whenever you explain things in this way, there's going to be some kind of connection between fields. And in the history of physics, it has happened several times. The simplest one is when people were looking at what's called thermodynamics. It's the theory just describing things that you can even have a sense for if you touch or feel. For instance, the temperature of your coffee. If you go on an airplane and you start feeling pressure differences in your ears, all these things that we call temperature and pressure, all these things are part of thermodynamics. And for a long time, physicists were just looking at steam engines and what energy they produce and what temperature do they give. But then at some point, some physicists started thinking, where are these quantities, these properties coming from? And then that was the sort of beginning of what's called statistical physics, in which you sort of try to go microscopically, or at least a little bit more microscopically, and you start describing the things that are actually making up your cup of coffee. If you have coffee, you have some molecules of water with molecules of caffeine and etc. And if you now start describing that system with statistical methods, you can at some point make some approximations. You can say, I have an enormous amount of an Avogadro number of particles. I zoom out and I look at larger distances, and all of a sudden you recover thermodynamics. And that connection between statistical physics and thermodynamics just allowed for a much better understanding of many systems across scales.
Also biological systems?
So biological systems is sort of a new frontier of physics. In the past, physicists have stuck themselves to what you call inanimate matter. So matter that it's not alive. There's of course a big thing when you say matter that is not alive, because it sort of assumes that you know what is the definition of life, and that's also a complicated thing. Let's say that it's not made out of DNA. And for a long time, and still physicists that's the traditional domain of trying to understand those forms of matter that are not alive. But in the past 20 years, it has been realized that it's possible to slowly start pushing physics towards the domain of living systems. Okay. And I cannot say that it can describe all the biological systems that you possibly have in mind, but it's doing pretty well in describing certain systems, like simple bacteria immersed in some bath of some kind of liquid, of water or something else, you can start describing the collective behavior of all these bacteria in that bath. You can also do the same with a flock of birds. You can try to describe the flock of birds using the same methods of statistical physics and theoretical physics. And there's always some kind of limitation of those methods, but they also give a pretty good understanding of the general features, of the qualitative features that can happen in those systems.
And what happened that you crossed into biology? Is it the question of being able to look at something that is not in equilibrium or something else? What happened that you said, because it's a new field, let's say?
It is precisely that kind of idea. Normally, what we call inanimate matter is always in equilibrium with its environment. It's not always, but that's how we like to think of it. So you can think of it as the individual constituents of that matter. They're sort of molecules, passive. They do what they do because of the laws of physics of the interactions. But when you go into biological systems or animal collections, then you have to sort of view the individuals as slightly different. They're not just particles surrounded by forces, but they have their own internal dynamics. So they burn, fuel to create energy. And this is what a biological system typically is. This is what we are. We have all these internal processes of consuming, producing ATP. And because we burn that fuel, we can perform our actions. So in that case, we're not a system that is always in equilibrium with the environment. We're actually out of equilibrium. And that is thermodynamically very easy to explain. Our temperature is typically 37 degrees or 36.5 degrees. While the environment can be of many other temperatures. So that is really out of equilibrium. When you're in equilibrium, you're really thermalized, or you have the same temperature as the environment. And for us, as living systems, that only happens when we die. Because at that point, we're not able to produce energy anymore to keep our sort of state, our human form. And so we thermalize with the environment. We become at the exact same temperature of the environment. And that is true. So people are trying, or physicists are trying to move or use their techniques to describe systems that are out of equilibrium.
And if you're interested more in that topic, I knew a little bit because I did have an interview on that. So I will share the link in the show notes about thermodynamics and systems out of equilibrium for the listeners to kind of explore more, because it's pretty deep in the discussion. But let's leave biologists alone, or the biological systems, and go back a little bit to physics, because I think you're the first string theorist on Silax. So, of course, a very easy question for me, probably difficult answer for you. What is actually string theory, so that people understand it finally?
There's maybe a more public answer and a more technical answer, okay? So the more approachable answer, that also was the idea of string theory in the very beginning, is that instead of that, physicists have kind of conceived their worldview for centuries as everything being made out of small little particles, okay? Whatever they are, if they're quarks, if they're electrons, if they're whatever, they're small little particles that we mathematically describe as points in space. And these points in space, they, bump against each other and they exchange other kinds of particles that sort of mediate the forces between them, the weak forces, the strong forces, the electromagnetic forces. There's a particle that sort of helps out, reaching out to these particles and say, hey, you have to bend a little bit to the side or to the other side. And all theories of physics are typically described in terms of those particles as points. And the most well-known sort of model of physics that we have is called the Standard Model of Particle Physics, that it precisely describes everything in this language that I just mentioned. Now, the idea of string theory is, let's suppose, this is not its origin, but let me portray it like that. Let's suppose that maybe things, or the small units that compose the entire universe, are not particles, but are extended objects. So objects that have one more dimension. And that means little strings. So in one dimension, that's what it means. And so you can start thinking about, let's try to describe nature by looking at the interactions between these strings instead of interactions between points. And what that has led us was to something that we now call string theory, that not only unifies the three fundamental forces of nature, the ones I mentioned, the weak, the strong, and electromagnetism, but also gravity as a force. And this is why people became very excited, because all of a sudden it looked like the whole of physics was unified, because typically that's how we divide the physics into three forces, the ones I mentioned, and the other one that we don't know what to do with it, which is gravity. And then all of a sudden these things work together. That's what string theory is a theory that fundamentally, describes things as little, or the units are little strings. Now, that was the easy answer. The harder answer is that it's not exactly only this. So, in fact, if we want to define what is string theory, we don't have a good definition in general. The definition I just gave you works in certain cases, in other cases, is totally different. And in fact, we know now that the fundamental objects that compose things in string theory are not only strings. They can also be sheets, so two-dimensional, or they can be three-dimensional or four-dimensional. And we call that brains. We have a name for it, a brain. But not a brain like brain in in the head, but brain with B-R-A-N-E, a brain. It comes from membrane. So a membrane is a two-dimensional object, but just brain, it can be any dimensional object that you can think of. And in string theory, all these things come together. So there's brains and there's strings, and they make up a whole zoo of different concepts and even theories that describe what we collectively call string theory.
Okay.
And there's many details there, but fundamentally that's it. We're not looking at points anymore. We're looking at other objects and their interactions.
And that theory holds, and it perfectly also unifies it with gravity, as you said. Gravity is now together with all the other forces.
Yes, so the theory holds. That's maybe depends on what you mean. It mathematically holds. Now, whether it experimentally holds, no one knows. Unfortunately, there's no absolute evidence for string theory, but we can discuss more about that if you also want to ask questions about quantum gravity. But the special thing about it is that all the particles that you can think of, they are sort of understood as excitations of this string. So you can really think, as a string in the guitar. So when you pluck the string, it comes with a certain frequency of energy, and you can, try to pluck it in different ways, or you can put your finger and then you change on the string and you change the frequency. So there's a very rich sort of frequency space that you can get out of a guitar string. And that's exactly the same as in the string of string theory. Depending on its energy, the way it vibrates, it can be interpreted at different particles. So if you would vibrate in a specific way, it would be a particle of light, the photon. And if it would vibrate in a different way with a different energy, it could be the particle of gravity that we call the graviton. And we don't know if it exists or not. No,
you hope.
Okay.
Maybe, I don't know.
Well, yeah, I hope. And I think the majority of physicists, not just string theorists, but the majority of physicists would think that there is such a thing as a particle of gravity. Even though you'll find some that disagree, but those are, I would say, at the moment in the minority.
Okay, so now I am a bit clearer on something, but then I'm more confused on other things, because, of course, I'm also thinking of quantum physics. And when you describe quantum physics, I never noticed that you were talking about strings in quantum physics. You talk about particles more, or not?
Yeah, that's true. So all those theories that I mentioned that physicists have come up with, for instance, the standard model of particle physics. So there we don't use quantum mechanics is an old thing now. Okay. So sorry that I have to go back a little bit, but quantum mechanics is something that worked for certain systems. Then when it got unified with what is called special relativity, it gave rise to what we now call quantum field theory. And quantum field theory is the theory of quantum fields. You can see pretty much everything in the universe as fields. Into it, there is what's called particle wave dualities that allows you to see these fields at certain points as particles. That's a longer story. But when you describe things with this framework that we call quantum field theory, which is based on quantum mechanics combined with special relativity, then indeed, we're talking about points. Okay. So now what string theorists did was, let's not talk about points, let's talk about strings and bring the quantum physics into the strings. And then when we look at what we call quantum strings, That's precisely when it happens that the vibrations of the quantum string gave rise to different particles. It's literally taking what we know from quantum and applying it to a different object rather than a point.
Okay.
If that makes sense.
Yes, it does. At least for me. We'll see what the listeners say afterwards. Right?
Okay.
I'm also expecting some physicists saying like, no, because there's always one physicist.
No, well, there's nothing. There's no
not to
the
this.
discussion.
Not to this. I'm talking about previous things you said.
Okay.
This I think is pretty.
Right.
Who knows? We'll see. But yeah, you mentioned gravity, so I also want to discuss that, right? Because of course, I keep comparing my discussions with different researchers who come and talk about physics to my school knowledge, right? And of course, at school, it has to be somehow clear. You can't teach people that it's all unknown, because then what would they learn, right? So there is a bit of the theories that we are sure of, and the rest kind of stays for exploration, right? And I always thought that, okay, gravity is kind of figured out. It's all fine. And I have a feeling that it's not, right? There is a lot of problems with it.
Well, yes and no. So this depends on what you're interested in. So to give a bit of context about what we know for sure about gravity today. So a long time ago, this person called Isaac Newton realized that the same phenomena of an apple falling from a tree or planets moving around the sun is sort of the same. Is a force that is somehow pulling things to its center. So in the case of the apple, you have the entire Earth pulling the apple down to its surface. In the case of the sun and the planets, you have the sun pulling the planets towards the sun. But of course, they don't come near it because they're also moving around the sun, and that prevents it to happen. So he kind of unified, apples and stellar objects, celestial objects, into one single theory that was called Newtonian gravity. And in this theory, what happens is that you see space and time as a sort of stage. A stage is fixed. It's metaphysical. It's not part of physics. It's metaphysical. You just say, let's assume there is a space and time, and our objects, like the apples and the planets and the sun, they're just, like the dancers or the actors on that stage. And the stage doesn't change. It's immutable. And everything that happens, all the physics, is just the relationships between those actors or dancers on that stage. Okay. But then a lot longer later came Einstein, who said, well, you guys got it wrong. Actually, the stage changes. The stage is not immutable. The stage is not metaphysical. It's part of physics. It's physical. And in fact, what he realized is that the objects or the actors or the dancers on that stage, they actually change space and time around them. They deform space and time around them. And so the theory of gravity became not a theory of forces anymore, but a theory of geometry, because the way you deform space and time, that has a geometric bearing, that the way that objects are shaped and the way they move, they deform space and time in specific ways. And then it was realized that it's not forces that pull things towards each other, but you just have to imagine yourself that you're, for instance, in the big deformation caused by a planet or by the sun, and somehow the other things that are slightly smaller, they would just fall in towards the sun because they're just following their own path. It's like when you have a mattress in your bed and you put a very heavy object on that mattress, it sort of sinks on the bed. And then if you put a very small other object, like a small ball, next to it, it will just fall towards the big object that you put on the bed. So that's what is happening. It's not a force. It's just following the geometry of space and time. This was sort of the sort of ideas that happen in gravity. And now there's not really a problem with gravity, in the sense that almost every single observation that I am aware of the universe, either of the universe expanding or of galaxies moving apart from each other, or the way light bends when it moves past a star or past a black hole, it's all compatible with the theory that Einstein has written down a long time ago. Even these new discoveries of the collision of black holes and the gravitational waves that come out of that collision and, propagate through the universe, bending slowly space and time as they reach the Earth, All those things are compatible with gravity, with the theory of general relativity. So then, is gravity not well understood? Now, what do you mean? It means that there are certain puzzles that are mostly theoretical about gravity, and that has to do with how does it operate, not at very large scales, even though some people also think there is some issues at large scales, but at the smallest scales. So when you start probing interactions, gravitational interactions, or the forces of gravity at smaller scales, okay, which we also call at higher energies. And there can be many problems. And that's why people started developing quantum gravity, because at those smaller scales, you're supposed to start seeing quantum effects. So you need theories of quantum gravity to try to explain that. And there's many things where they can show up. So, for instance, you need to understand these effects if you want to understand what happens near black holes, what happens to the information that goes into black holes. Does it come out again? What happens to what's inside the black hole? What is inside the black hole? We have no idea. What happens to the singularity that is supposed to be inside the black hole? Is it formed? Does it exist? Does it not exist? These are all theoretical puzzles because we have absolutely no way of observing them yet. So there are certain expectations that maybe there are modifications of Einstein's theory that could be probed by gravitational waves or by telescopes like the Event Horizon Telescope and things like this. But there's absolutely no issue with the theory we have. So there are certain things we don't know where they come from, like the universe is expanding. We call that expansion is sort of driven by what Einstein himself called the cosmological constant. We don't know how did it came to be, but we know that if we include it in Einstein's theory, everything works. We don't know what dark matter is, but we know that if we put something in the Einstein's theory that behaves like dark matter, then everything makes sense again. So there's sort of things there that we don't exactly know where they come from, but at the same time, for the observations we're making, there's absolutely no problem with gravity. If so,
okay,
so
it makes sense. I mean, I've discussed enough to know that not everybody says it this way, but I understand also where you're coming from. You've asked me a lot of questions, and I also realized, and this is always my problem when I'm really fascinated with what the guest is saying, I don't see the time flying, and my listeners are kind of used to the fact that the pop quiz question is asked more or less in the beginning of the thing, and I'm thinking, it's 30 minutes. I've made it again. So anyway, listeners, if you've been waiting very patiently, thank you very much for waiting. And now it's the time for Jay to ask the question. This means also that we will solve it a bit faster than the usual. So yes, another question for you. And that's a difficult one, actually, at least for me. Maybe you will know. So Jay, can you ask the question? And yes, solving it only at the end.
Right. So the question is a water molecule wet, and is gravity wet?
Okay, perfect. Answer at the end. And I mentioned that you asked so many questions. So I was thinking, okay, you as a researcher, as a scientist, you wake up in the morning, and which of those questions are you trying to solve? Or is it something else? Or is it that emergence you were talking about in the beginning?
I don't think there's an easy answer to that. I mean, I don't have a constant sort of answer. It depends on what I'm interested at the time. So, in fact, I'm not actually trying to solve the puzzle of quantum gravity all the time. What I'm trying to do typically
just on Fridays. On Fridays you try, and then you
on Fridays I could think a bit more about it. Yes, that's true. But on Mondays, or on what's day today? On Wednesdays, I typically think about how to apply methods that are coming out of string theory to other fields of physics. Typically, this is sort of what I'm thinking. Sometimes it just stays within string theory. Sometimes I don't go around. I just try to solve a problem within string theory, and therefore exploring a bit what this big theory of quantum gravity is. But many times I'm just thinking about how to describe collective phenomena in different materials, in different exotic phases of matter, different sort of rearrangements of microscopic constituents that give different properties at macroscopic scales. Or sometimes I'm thinking about living systems, or sometimes I'm thinking about how to model social systems with the exact same methodologies. This is what happens. It's totally random. It's how I feel that day.
But then you also
Yes.
have to put it into publications, right? I'm leading to
Sure.
something, I love talking to scientists who do also science communication, because I know that
Yes.
it's not going to be so much on me to explain what they're saying, because they are trained in explaining things. But then again, as I was writing to you, I looked into some of your publications. I tried to read them even. And even from the title, I mean, I couldn't get abstract. I couldn't get anything. I mean, I have no idea what you're doing, really. I mean, listeners, listen to this. I
Yes.
mean, I did write it down, so I have to say what you are trying to do in one of the articles. We formulate
Okay.
the theory of nonlinear viscoelastic hydrodynamics of anisotropic crystals in terms of dynamical Goldstone scalars of spontaneously broken translational symmetries under the assumption of homogeneous lattices and absence of plastic deformations. I mean, please, do you actually try to explain this as well when you're explaining now? No, probably that's too deep in.
No, it's actually not. But you need to use different kind of language, I think, or you
In
need
order
to
to sound
explain a little
scientific,
bit
right?
what.
Otherwise, people will not
No,
treat you
no, not to sound
seriously.
scientific. No. You have, so the papers typically in this field of theoretical physics, they're always technical like that. And it would be impossible to just take that and sort of explain to a general public, even when it's difficult to just explain to other physicists in other subfields. So you need some time to explain things, okay? But if you want a very simple or simpler explanation of what all that means, is that matter organizes itself in different phases. You can take the example of water. If the temperature is too cold, it's going to be a solid, a crystal, ice. If it's sort of a bit more warm, it's going to be a liquid, and even warmer is going to be a gas. All these sort of things, all these characteristics that come along with it, we call each of them a phase of matter. So ice, a crystal is one phase of matter, is a solid. The liquid is another phase of matter. And in general, everything that we know of organizes like that. We can come with different names. These names you might have seen, they have technological applications. There's superconductors, there's superfluids, there's ferromagnets, there's crystals, there's metals, there's everything that you can think of, and even more exotic things that people can sometimes build in the lab. Now, the way we describe those phases is using a concept of symmetry. What symmetry does each form of matter has? And we know that, for instance, ice, a crystal, it kind of breaks what we call translation symmetry. So if I'm here and I move slightly to the side, if I have translation symmetry, it means that nothing changes when I move slightly to the side. But the idea of a crystal is that you have these atoms that are really organized in what we call a lattice. They're very, can be very regular. There's an atom here, there's some space, there's an atom here, then there's some more space, and there's an atom there. And so if you just move a little bit, you end up in empty space. And that means that, actually that the symmetry, the translation symmetry is broken. Okay. So that's a way of classifying matter. It's by their symmetries. And there's sort of crazy symmetries that people have conceived over the years. Translation is a simple one. Rotation. So if you rotate yourself, nothing changes. That's another symmetry. But then there's crazy symmetries that come with different names. So there's higher form symmetries, there's higher group symmetries. There's a lot of bunch of symmetries that you can use to actually classify matter in a simple way. And the way we sort of use those symmetries, so we take those symmetries and then we build a theory that describes the dynamics of that piece of matter. So if I have a table, which is supposed to be in the solid phase, it's a table, and I hit it with my hand, I'm going to create some deformation in that table that propagates through the table with what we call elastic waves. Okay. So there is a theory that will describe that sort of propagation that we call the collective phenomena of that table. And that theory is called the theory of hydrodynamics. It's the same theory that describes what happens if you throw a rock onto the lake and the lake starts making water waves on its surface. So it's exactly the same theory. And what people realized in string theory, and that's and that's the leap of faith that maybe it has to be described, is that black holes, different types of black holes, behave exactly like that. So if you throw a rock to a black hole, it behaves as if I had thrown a rock into the water. Okay. And so a black hole can behave like a liquid or a fluid. But there's also black holes that can behave like solids. They're different black holes. They're characterized by different fields, different things, that somehow when I throw a rock onto that, it looks like there's an elastic wave propagating on a table.
Wait. So black holes are not all the same?
No, they can. I mean, no, not well. In theory, no. In observation, probably yes. So at the moment, everything that we know of in the universe, there's only one black hole. Okay, it's a black hole that has a mass and has a rotation. And it's very likely just a sphere. It's spherical, okay, that is rotating. Now, when you go into string theory, many other things can happen. There can be black holes that have infinitely extended directions, okay? So we go back to the idea of these objects that I mentioned at the beginning, the brains. So they can have infinitely extended directions. They can be strings, they can be membranes, they can be brains, okay? And these ones, these black holes, when you wiggle them, they behave exactly in the way that I've described. So this other word that you saw in the title, holography, is a duality between a theory of gravity and another theory that can be a kind of theory of particle physics or something else. And that theory is sort of behaving as if it was a fluid or as if it was a solid or as if it was a metal. While, on the other hand, you have just gravity, a black hole wiggling, but far away from it, it just looks like it's a theory of materials. So that whole thing there is to describe the physics of solids using gravity.
Okay. Listeners, what do you think? Did he manage to explain it or not? I think some of you are now rewinding to listen again. No, but congratulations. That was not an easy task, for sure. And I actually wanted to ask you on this, because you did write a book with very, very learned people answering your questions. How did it go? Right. I mean, you know which book I mean, the one about...
Yes, it's the only one I wrote about physics.
Exactly. So how did it go? Because, I love to know how it is to sit in my seat, if you want, asking questions to scientists. Did you ask them questions and then you just got the blah, 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 and it's like, oh God, I have no idea what they're talking about? Well, you're still a specialist in the field, so it was okay, right?
Yes,
or were you trying to say, listen, guys, let's make it a bit easier, because even no, they were too important to say that, right?
No. I mean, I did try in the beginning when I approached them to ask them to sort of make their answers as less technical as possible. But because the topic is so technical, it's just very difficult to do that task while still, wanting to talk about the details and the differences between things. So in the end, it ended up being rather technical. But at the time that I started, which was like, I think by now 15 years ago or something, I was still a PhD student. So I was slowly becoming a physicist, but I was definitely far from a physicist. So my understanding of many of the things was not very good at all. So I had more of a role of a journalist, like you are having now, rather than a scientist. And I went there with a big bunch of questions every time, with maybe 90% of them I didn't know the answer to. I did become a lot more critical as the years passed, because it took 10 years for me to complete the book, and some of the interviews were much later. So at that time, I was already a more, well-rounded physicist, and I could be a lot more critical, but I could also, understand a lot better. And so you can really see a shift between the quality of the interviews from the beginning to the end. Yes, you can.
And because the field is changing so much, if people read it right now, is it still valid, let's say, the theories that are discussed?
Many things are still valid. Yes. So a lot of it was about also the status of things at that time, of what is the understanding of theories of quantum gravity at that time. And that thing will be invaluable no matter what. Now, there are certain discussions that were at the time very heated that are less heated up at this point because perspectives have changed on the importance of those questions or even in the validity of the question themselves. So many things have changed over time, but the core ideas and the core results, that is sort of there as a historical record. And if you want to sort of understand as a student, so it's really not for non-experts, if you want to understand things as a student of what is the state of affairs of quantum gravity, you know that it's a perfect place to start, even though in the past 10 years there has been enormous amount of developments in certain topics that were discussed there. And so what it means is that there should be a volume 2 with another round of physicists, with another round of questions to try to, record the history at this very moment. But that doesn't invalidate the history back then.
Good. I get it. So I also understand that it's not a book for me. So it's fine. No joking. No, because I was trying.
Yeah. No, I don't think so. I wish it was in the beginning, but it didn't turn out that way.
But it's interesting from that point of view as well, because, I am a little bit tired of the Schrödinger's cat, nothing personal about Schrödinger. But when we talk about quantum mechanics and the basics of it, it's always the same analogies, It's good. It's good we have these analogies. But of course, when you're explaining science, it would be nice to have different ones. And I noticed that people are trying to figure out something else. But with quantum gravity, you get really deep in. And as you're saying, you could wish that you could find good analogies, especially if you're talking about something that is not observable. So, the intuition of an analogy is something you can imagine, you can see. And here, I don't know. Right?
Yeah, there's less. There's still Gedanken experiments, that we like to call it, or analogies. There's still some that can portray at least the difficulty of quantum gravity or some of the things that you expect from quantum gravity. So, for instance, if you want to understand why, in principle, there should be a minimum scale, a minimum size of things that you can actually observe, you can think very simply like this. So, when you want to observe something, typically you have to send a signal and receive it back. So if you want to know if an object is somewhere, we send light with a flashlight, it hits the object, it comes back, and we see, okay, it's here, right? And this is the whole principle of almost every single observation in physics, is that you either receive the signal coming from somewhere, from the flashlight, like a star, or you send a signal and wait for whatever it comes back. But quantum gravity is about the smallest possible scales, distances. And to probe the small possible scales, you have to put more energy in. You have to keep on putting more energy and more energy and more energy to see smaller and smaller and smaller distances. But the problem is that at some point, you put so much energy into it to see very small distances that the amount of energy concentrated in a very small region of space and time creates a very small black hole. And at that point, if you keep putting more energy in, the only thing that happens is that the black hole will get bigger because it starts swallowing the energy. Of course, this is an analogy, but it tells you that you expect that if things work the way we think they do, that there's space and time, and I keep on observing by putting more and more energy, there's going to be a fundamental limit to that observation. Or the physics has to be radically different at those scales. So either way, there is something else that is going to replace our knowledge of things at small scales, and that is the theory of quantum gravity. So there is, analogies like this that probably you think are not too bad to explain what's going on.
Thank you for saying what I think, but yes, I would agree. Okay, you keep mentioning black holes, so I think it's good to finish with black holes. I mean, I want to talk a little bit also about research in the Netherlands and Denmark and all that, but first of all, black holes as such. I think this is a very sexy topic in general. I mean, it's one of those topics, in general, space is really cool as a research subject because it just works on our imagination, right? Do you feel that as well, that people get excited about black holes?
For sure. Yeah, they're some of the most exotic, or the most exotic object that we know that is out there in the universe. And there's a lot of things we don't know about them, at least theoretically. Yeah. So it's a very puzzling thing that has a lot of weird phenomena. And of course that sort of makes you wonder. Also because, it also makes you wonder because we don't know what's inside it.
Yeah.
And that also gives rise to an enormous amount of speculation that sort of fuels imagination. Some people think about different worlds inside a black hole, that you go through it and you end up in a white hole in another universe. It fuels a lot of imagination and sci-fi, which is really fun. So of course, yeah, I can understand the sort of excitement about it.
You're a theoretical physicist, so I understand you're more on the what could be side. But I wanted to know just from you right now, what do we actually really know about black holes? Because I'm a bit confused on where's the line of where spaghettification, for example. We're sure that's what happens to the matter when it goes in. It just gets spaghetti. No,
I don't think. We've never, probed things so close to the event horizon to know for a fact whether things are spaghettified. So spaghettification is something that you think, again, is one of these sort of analogies or Gedanken experiments in which, you think about the black hole as totally isolated from something else. There's only the black hole and nothing else. And you have a person that goes towards the event horizon, but somehow that person has the feet a bit more in front than the head. And because the gravity is so strong, it will pull your feet so much compared with your head that you get spaghettified. Theoretically, it sort of makes sense. But whether that happens in reality, I don't even know, because typically even black holes don't exist in isolation. They have a sort of environment around it, which is typically what we call the accretion disk, or everything that forms galaxies. So there's a bunch of matter that is moving around black holes, and very close to it, it gets hot because they're moving a lot faster, they're colliding a lot faster. There's supposed to be strong electromagnetic fields. I have no idea what happens if you just drop a body right there at that very moment. But what we do know about them is that they exist. Okay, we've observed them. They're almost, or as far as we know, maybe there's cases where this doesn't hold precisely, but almost every single galaxy that people have found, there's a black hole in the middle. Okay, so this is super important for the formation of galaxies itself. It's like the sun of our solar system, but it's the black hole that has so much gravity, pulls so much things towards it, that it is able to have all the stars and the planets in the galaxy moving around it as the planets are moving around the sun. So we know these guys are there. We've observed them. We know that light bends around black holes. So that's called gravitational lensing that exists. We also know that light can get trapped around black holes. It can circle around a lot of times before it reaches the observer or us on planet Earth. We know that certain things, that light happens to be trapped there because we have taken a picture and we see the sort of light rings around the black hole in these classical images of the Event Horizon Telescope. We know this is there. We know there's supposed to be an event horizon, but we don't know exactly whether it is an event horizon, in the sense that what happens when you enter. This is not, is that an event horizon really in the sense we think about? Like, I could enter through it and something happens inside. Or is the thing that replaces inside the black hole, the thing that the inside is replaced by some other kind of matter that we don't know? That, maybe string theory has something to say, maybe it doesn't, who knows? But something else could happen there. There's ideas that, some people call firewalls. So you enter and you just die because you collide with something. To the extent that this is an event horizon, we don't exactly know, but it sort of behaves precisely as if it was an event horizon. And, things seem to be falling in. Black holes can grow. Stars and planets next to it, they fall in. What happens exactly, we don't know. We also know they can sort of send jets, bursts of energy, which are the largest structures that we have ever seen in the universe. So they can be just jets coming out of it near the center of the galaxy, so near the black hole. The process by which that happens is not exactly fully understood, but some people think it has to do with the large magnetic fields around the event horizon, and then particles that are part of the accretion disk or the matter that surrounds them get accelerated by those fields and shot into space. So that's one possibility. So these things we sort of know. We also have a lot of statistics for the mass of black holes. We have a lot of statistics also for the angular momentum, or how fast they rotate. And that's pretty much it, which is not bad because it's already a lot, and we have a picture. So it's a lot.
I don't know if you will know. You say we have a lot of statistics. So just to imagine as well, what is the average size of a black hole?
Actually, I don't know the average size, but it should, they can vary between, something like 10 to the 6 solar masses. Yeah. It's not that tiny, but compared with the accretion, the matter that surrounds it, it's small because it's really just the center part. Yeah.
Okay. It's a bit of a risky thing to move from black holes to doing research in the Netherlands, but I have to do that because as now in this season, I will have a chance to talk to different researchers in different places, in different academic centers. I'm also curious, how is it to do science in the Netherlands and how is it in Denmark? Because you have experience in both. Do you see differences or it's just, it's academia, it's all the same?
Well, I do see differences. I think the biggest difference that I see is the way that certain funding schemes are set up in different countries. And the Netherlands has had a focus, not only at the university level, but also at the national level, on interdisciplinarity. So there's many programs that you can apply to create interdisciplinary teams that go beyond a single discipline. This is something that maybe is showing up slowly in Denmark, but it's not yet there to the same degree at all. So the idea that interdisciplinarity is important to solve complex societal problems or just complex problems in general is something that is becoming more and more predominant in the Netherlands. And, in which you can bring not only the physics, but the physics together with the math and the chemistry and the social sciences and the economics and all these kind of things. Is something that is sort of growing there compared with Denmark. So there's more exchange in that way between fields. That's my impression. And the other thing is the societal engagement. So the funding agencies in the Ministry of Science in the Netherlands compared with the Ministry of Science in Denmark is also very different. There has been more emphasis in the Netherlands on both societal challenges. How can you actually help certain societal problems with your science, but also societal engagement. Can you engage people in a way that can even be part of the method or the scientific process itself? So things like, citizen science or gamification or exchanges of other forms. There has also been emphasis on exchanges with art, but also a lot of emphasis on, can you actually use the methodologies that you have in your hardcore science to, solve the problem of climate change or to solve the problem of the energy transition or something like this. And also emphasis on industry application. So can you actually develop things that will benefit society in a specific way? So this kind of moves toward that kind of interdisciplinarity and societal application and engagement seems to be very different from what I experience in Denmark, which is still very much grounded in sort of the core sciences and that development. You could also say there's also an issue of numbers. Netherlands has 70 million, Denmark has 5 million. So there's also, I suspect, a sort of a limitation for what the different funding instruments can have. But I find the Netherlands, and especially in my field, is also, there's a lot more exchange. Also, it's much larger. There's a lot more exchange between scientists. I don't want to be so negative about Denmark, but there's a difference in degree in these exchanges. Yes.
Do you actually see also the difference in interests, public interest in science because of that? So because you're saying that the citizens are more involved.
There's a sort of a movement towards that, but I don't know if citizens are more involved in general in terms of numbers. So there's statistics I do not have. But I do see both countries equally involved, at least equally interested in science. That I'm not sure there are differences in that regard. Especially because, I have some experience in organizing large-scale events for reaching out to the public. And I can see that sort of interest in those events, it doesn't change whether it's Denmark or the Netherlands. So I think the interest is definitely there. The initiatives to engage them as part of the process, that probably is lower in Denmark compared to the Netherlands. But I don't have the statistics.
After the serious discussion about doing science and science communication in different countries, we have to go to a probably equally serious solving of our pub quiz question, because I'm super curious. I can't wait. I waited for 20 minutes. So now it's the time to actually solve it. So what was the question once again, Jay? And then please give us the answer.
So the question was whether a water molecule is wet and whether gravity is wet. The answer to the first one is no, a molecule is not wet. And to the second one, is gravity wet? The answer is maybe. So maybe it comes with explanations.
Yes, it does, for sure.
Yes, okay. Okay, so wetness is is an emergent property of the collective of molecules of water. So a single molecule is not wet, but when you put a lot of them together, then it can be in a phase that we call a liquid. And then that thing has the property of wetness that you feel. If you put your finger in a glass of water, it sort of adheres to your finger and it can sort of move. So that sort of property is what you would call wetness. But it's a property of the collective. It's not of the individual. Okay, so there's many properties like that. Those are sort of the emergent properties of matter. Now, in a black hole, I did mention, it was not so maybe it didn't take enough time, but I did mention that there is sort of this duality between gravity and theories of matter. So if we would ever see a black hole that would sort of share some of the properties that string theorists say they might have, okay, if we would see that, then there is a sense in which I can describe that black hole as a theory of fluids, okay? And in that sense, they have some kind of property that would resemble wetness. Yes.
I just love the answer. There was a lot of it seems and conditional might, if ever. Yeah. Very sciencey, yeah. I have to say.
Yes. So the second one, I agree, it's a lot of speculation. Yeah. But maybe.
Yeah. But it's possible. It's possible. Maybe, yes. If ever, whatever else. Okay, good. Maybe one day, exactly. Maybe one day we'll meet again, and then we will say, yes, we have proven, we have seen, or whatever else. Or maybe you will just say absolutely no to the pub quiz question. It's a direct no. It's not the case. So yes, hopefully we will meet again one day and discuss, like in 10 years, like with your book. In 10 years' time, we see where you are.
But, it might take longer than that.
Yeah, I guess. I mean, I wanted to be ambitious, but fair enough. And what remains is to thank you, Jay, so much for today. It was a fascinating story. As you can see, listeners, I forgot to ask the pub quiz question earlier because I was so interested in what Jay was saying. Thank you for coming and sharing a small part of your world with us.
No, thank you.
And this is it for today. Don't forget to subscribe, to follow us. Remember, we are on Patreon, so you can support us as well. And then if you become a paid member, you can also suggest guests and talk to us and just, interact more than the usual. We are present on all the social media, so also check that. This was Silax, and my name is Hanna Siemaszko.